Hello there, and welcome to office hours for the University of Vermont course CS 206, Evolutionary Robotics. This is also the office hours for Ludobots, the online course that is run out of Reddit. Just as a reminder, the course home is located at reddit.com/r/Ludobots. As always, I'm happy to field questions. It's currently 3 o'clock Eastern Standard Time here on the East Coast of the United States. If you have questions, ask them at any time, and I will do my best to answer them. And if there are no questions, I'll go over various issues that tend to be a challenge for students in the class. While we're waiting for a question, just to orient the online students as to where we are, let me bring up the current schedule of the course. We are currently about a third of the way through, and we are working our way now through. A history of the field. We just finished last Tuesday. I'm sorry, where are we now? We finished last Thursday talking about CTRNNs, or continuous time recurrent neural networks. These are a particular kind of artificial neural network. And the Tuesday before that, we talked about the first few years of evolution in robotics and the first experiments. As always, if you want to follow along with the lectures, there have been 8 so far, and for each of the 8 lectures, there's an associated video that you can go and watch on YouTube. Let's see, what else can I tell you? We are on Tuesday, tomorrow morning, we're going to be talking about minimal cognition experiments. Again, I will tape the lecture and put the video up online. There's some reading there for you as well. For the undergraduates in the class, you're currently working on assignment 5, and graduate students are working their way through assignments 9 and 10. So for the UVM students, assignments 5, 9, and 10 are due at midnight tonight. For the online students, as always, you can follow along the course at your own pace. Submitting solutions to the assignments is completely optional. Okay, while we're here, let me just talk very briefly about, I've shown you the schedule. Let me talk a little bit now about assignments 5, 9, and 10. So let me open up assignment 5 here for you. In assignment 5, you're actually going to be doing 2 smaller projects, so 5A and 5B. 5A is refactoring your code. For those of you that are not familiar with software engineering, refactoring is a way of cleaning up your code and making it more modular. And by making your code more modular, it's easier to comment in and out different functionalities and test each part of your code in isolation. Most of us have had the experience of writing one long monolithic piece of code. And it's very hard to sort of pick apart where an error occurs when it does. So by refactoring your code, you're able to, again, break up your code into smaller and smaller independent chunks, and then isolate when your program crashes which chunk in that code is causing it to crash. So I don't think I'll talk any more about 5A. Let's talk a little bit about 5B, which is random search. So I will bring up the actual random search project here on the course website. So in this course, in the middle of the course, you're going to be, once you've created your robot, which most of you have probably finished by now, you create your robot by adding objects, joints, sensors, neurons, and synapses. We pause in assignment 5A to do a little bit of refactoring. And then in the next few assignments, you're going to be adding in increasingly sophisticated search algorithms that are going to search over the space of all possible robots to find the one for you that does whatever it is you want your robot to do. So we're going to start with the simplest search algorithm, which is random search. You can probably guess from the name how random search works. Creates one robot and simulates it, throws it away, creates another robot at random, simulates it, throws it away, and so on. So not too much to the to the random search assignment. I don't think there's anything really of note to talk about here, so if nobody has any questions about assignment 5, I'll move on to assignments 9 and 10. Okay, back to the schedule. If you scroll down a little bit, you can see assignments 9 and 10 are available here. Okay, so in assignment 9 of 10, you're implementing the genetic algorithm, which is probably the most high-powered search algorithm we're going to implement in this course. If you know something about evolutionary algorithms or machine learning in general, you're more than welcome to rip out the genetic algorithm after you've implemented it and replace the GA with a more sophisticated search method. Just to show you here, at the top of the genetic algorithm assignment is some pseudocode, which will show you what you're implementing in this assignment. It's a good idea to read this through and get an intuition for exactly how a genetic algorithm works. Okay, so that's the genetic algorithm. If nobody has any questions about the genetic algorithm, which is assignment 9, I'll move on to talking about the 10th and final assignment. So far, so good? Okay. All right, let's move on to assignment 10. In assignment 10, you're going to be replacing your minimal robot, which was the sort of scissor robot, with a more... Oh, I'm sorry. No, I misspoke. Assignment 10 is the phototaxis assignment. So let's jump to the phototaxis assignment. So what is phototaxis? Well, phototaxis is a behavior seen in a lot of animals, which is that they move in response to light. So in the case of moths, they're positively phototactic, meaning they move towards light. And you can all probably think of some insects that move away from the light, like our good friend the cockroach. Okay, so you're not going to be creating insects in this assignment. You're going to be taking your quadruped, which you developed in an earlier assignment, and evolving it to exhibit phototaxis. Well, what does that look like? Here's an example of the quadruped evolved to perform phototaxis. Just pause this for a moment. You can see, I'll pause this and roll this back. You can see here's our quadruped down here at the origin, and here is the light sensor, a light source in its environment, which is about 10 body lengths ahead of it. And the goal is, and the robot is now equipped with light sensors, so it can detect the light intensity that's being given off by this light source, and the robot has to try and move towards this light source. What's different in this assignment is you're going to take every robot, and every robot is going to be evaluated 4 times. The first time it's going to be evaluated in that environment, second time in the second environment where now the light source is placed on its right-hand side, and you can see that our robot is turning towards this light source and moving towards it. I'm going to show you the robot placed in the third environment where now the light source is behind the robot. This is all the same robot with exactly the same neural network turning and moving towards the object behind it, and completely failing to detect and move towards the light in the fourth and final environment. Okay, so that's phototaxis. So up till now in all the assignments you've been evolving one robot in one environment. Now in phototaxis you're seeing how to evolve robots to exhibit robust behavior, meaning that they need to exhibit their behavior in multiple environments. Okay, so that's phototaxis. After this, for the UVM students, you're done. This is the 10th and final assignment. You will then have a number of weeks to take your basic evolutionary robotics simulation and test a new kind of project, anything you like. In class tomorrow morning, we will talk about possible projects. So for the online students, if you're interested in the kinds of projects you might be able to tackle with your simulation, after tomorrow, go and have a look at the video lecture for lecture 9, and at the beginning of that video lecture, I'll talk about projects you might want to tackle. And in office hours in the coming weeks, we will also go through some of these possible project ideas. So one of the things that I will try and help you with is trying to pick a project that is sufficiently interesting, but is also feasible within a 6 or 8 week period. For the online students, of course, you're free to pick as ambitious a project as you like. Okay, no questions yet, no questions about the assignments. So let's move on and talk a little bit about the phototaxis, about evolving phototaxis itself. Evolving a robot to perform phototaxis is very tricky. It's not an easy thing to do, and you might have actually seen why it's tricky to do. Let me go back to the actual video here. So in the video, remember this is an evolved robot. You can see it does pretty well in the first 3 environments, but in the final environment, doesn't do very well. Okay, so you might be able to evolve your robot to do well in 1 or 2 or maybe 3 environments, but very hard to get it to do it in all 4. I see that there is a question, so let me just pause here for a moment. In assignment 10, is it good or bad if my robot has very strong phototaxis? The fitness is higher than 0.35, not like others. So I'm assuming you mean by others like random robots. So if you take a random controller and drop it into the robot in these 4 environments, I think it does tend to get a value around 0.2. I believe that's what the student here is talking about. So yes, so if you can show us that your robot's fitness is significantly higher than what a random robot would get, that would be perfectly sufficient. That's fine. Okay. Okay, so actually this is a good question because I'm going to talk a little bit about how to actually do a better job of getting phototaxis. So for the UVM students that are submitting this assignment for credit, again, to show that your robot is doing something significantly better than a random robot would do, that's perfectly fine. We're not looking for perfect phototaxis in this assignment. But after you put in some effort to actually really try and evolve phototaxis, you probably want to try and get your robot to do as good as possible at this task. So how do we do that? I'll show you a few tricks about how to do this. The first one to take into account is that something that's working against us at the moment is what's known as the inverse square law in physics. This is a little stub to the Wikipedia article here. So imagine that our robot is sitting somewhere out here at the origin, and here's the light source, about 10 body lengths ahead of it. Clearly, the further away it is, there's relatively little light falling on our robot, but the closer it moves to the object, there is not just more light, but twice as much light, right? So as the robot approaches the light, the amount of light actually falling on the photo sensor increases quadratically to the power of 2. So if you think about it, imagine we have one robot sitting here, and it moves forward in one environment, and then when the light source is over here, it moves an equal distance away from that light source. That robot is going to do very well because as it moves towards the light source, it's sort of eating up a huge amount of light, and it's not being punished so much for moving away from the light in another environment. Let me pause here for a moment. The student XC is clarifying their point. Sorry, others means it's not like the result from other students. Some of my friends only got 0.15 to 0.17. Okay, for your friends that got 0.15 to 0.17, that doesn't sound like phototaxis to me. So I would say it's definitely good for you if you're getting 0.35. The way we are going to assess this phototaxis assignment is really from the video. So we can see that your robot is approaching, if one robot, your evolved robot, is approaching the light source in 2 or 3 out of the 4 environments, that's the real proof that you're giving us that you correctly implemented this assignment. We're not really too interested so much in the actual fitness values. So for your friends that are getting 0.15 or 0.17, I would motivate them to check their code and make sure that they have actually implemented the phototaxis assignment correctly. Okay, so back to the inverse square law here. So again, you can imagine, in a sense, a robot getting greedy, quote unquote, because it might evolve the ability to move really close to the light source in 1 or maybe 2 environments and collect a lot of light, because light goes up goes up quadratically as it gets closer to the light source, and the robot doesn't care if it moves away from the light source in other environments. So how do we motivate our robot to do a good job at this task? Well, let's go and have a look at the code for a moment, and I'm going to bring up, let's see here. I will attempt to bring up here some code for you. Okay, let's have a look. This is the individual.py file. So this is the individual class. And you remember that the individual class contains a genome and also the fitness of the robot that was produced by this genome. Okay, so this is where the fitness is stored for our robot. And we compute the robot's fitness in this function, compute fitness. And in the assignment, what we tell you to do is to set the robot's fitness initially to 0, and then in each of the 4 environments that any individual robot is evaluated in, we sum the current fitness. So the current fitness is equal to the last light sensor value just before the end of that evaluation trial. So we're summing up fitness, and then away we go, right? So let's change this now to something else. So I'm now going to change this to sum up the log of the current fitness. So why the log? Well, what the log means is that if in one of the 4 environments the robot gets a very high current fitness value, it travels far towards the light, travels close to the light. Remember, there's much more light falling on it. We take the log of that. So it's sort of like you get some reward for traveling close to the light, but you get less and less reward as you get closer. So there's more motivation to get somewhat close to the light, but also to make improvements in the other 3 environments. Okay, so now we're taking the fitness of any given robot is the sum of all of its fitnesses in the 4 environments, and it's actually the sum of the log of each fitness component. Okay, so that's the change we've just made to the code. Let's actually run this and see what happens. Okay, so let's see. I'm going to run my genetic algorithm, but I won't run it for all 100 generations because we'll be here for a while. So let me stop my code here for a moment and make another change. Okay, I'll come back to the code here. I'm going to open the constants file. In the constants file, this is now where I sort of set how my genetic algorithm runs. We evaluate each robot for 500 time steps. We evaluate each robot in 4 different environments. And we create a population with 10 robots, and we evolve that population of 10 robots for 100 generations. Let's change this to 50. That should be good enough. Okay, I think we can wait for it to get to 50. Okay, so you'll notice something strange now when the code is running, which is that the fitness values happen to be negative. And if you think about this, you'll know why these fitness values are negative. It's because we're taking the log of the distance, and that distance tends to be, as our student XC pointed out here, tends to be less than 1. So we tend to get values that are negative. The first robot in the population of 10, so you'll notice we have 10 robots here, right? The first robot in the population is always the best one. It's the highest value of all 10. And if you look carefully, like for example here, you'll see that the value is going up slightly. Doesn't seem to be going up very much at the moment, so maybe this robot isn't doing that good a job. Oh, it's gone up a little bit. When we get to 50, we're going to play back this best robot that we found after 50 generations. And when we play back this robot, I want you to watch and see how well the robot does in each of the 4 environments. Is it a specialist, meaning it does really well in one environment and terribly in the other 3? or is it on the way to becoming a generalist, meaning it's doing a pretty good job at all three? Okay, here it is in first environment. Not doing a very good job at all, going in the wrong direction. Now the light source is off to the right. Still not doing great. Third environment where the light source is behind the robot. Pretty good here. And let's see how it does with the object off to its left. Not very well at all. Okay, not a very successful run. I think that if you run this for longer with a larger population, you might have a little bit more success with this robot. So try, for those of you that want to try and get better phototaxis, run your robot for a while and sum up the log of the fitnesses rather than just the fitnesses themselves. Okay. Okay, there's another student, MoVH, who had a question for me earlier. She has sent me an email. She's having a problem. Let me see if I can bring up her the issue she's having for you, and maybe we can debug this together. I'm just reading her email here. Okay, so MoVH, I think this is going to be difficult for me to debug your issue online. Hopefully we can talk after class tomorrow morning. As the UVM students know, they need to submit their assignments tonight. So you can either go ahead and submit it if you think it's working. If it's not, you can hold off. And if you come and see me during my in-person office hours tomorrow, come and see me in my office hours in person tomorrow, and we can try and debug this face-to-face. Okay, so we'll leave that for now. So we've talked a little bit about the schedule, assignments. I've given you a little bit of a hint about how to improve phototaxis. Just for fun, since we've got some time, let's make another change in phototaxis. So I'm going to bring back my code here, and let's open up individual.py again. And we changed, if you'll recall, we changed the fitness value here, so we're summing up the log of the fitnesses. Let's instead reward robots based on the worst of their 4 environments. Well, how do we do that? Remember that we're going to get fitness values back. We're going to get 4 fitness values back for every robot, how well it did in each of the 4 environments. We're going to look at the 4 values, and we're going to set self.fitness equal to the worst of these 4. Okay, so how do we do that? We need to first go to population. And in population, when we evaluate every individual in the population, we first iterate over the population and set the fitness of every robot in the population to 0. Now let's start by setting the fitness of every robot to a very, very high value. So innocent until proven guilty. We'll assume that every robot did really well. And now when we iterate over each robot and each robot in each environment, we're going to look at how well it does in each environment. And if the fitness from the current environment is worse than its overall fitness, we set overall fitness worst equal to that worse fitness value, right? So if it does really well in environment 1, it's still going to be less than 1,000, so we'll set fitness equal to how well it did in this environment. If it does better in environment 2, fitness 2 is going to be higher than fitness 1, so we throw fitness 2 away. If it does worse, way worse in fitness 3, so fitness 3 is lower than fitness 1, then we're going to replace fitness 1 with fitness 3, right? We're taking the minimum value. So in order to take the minimum value, we set the default value to a very high value, and then if we ever see a value below that, we replace it with that value. Okay, so we set it to 1,000. Let's go back to individual now and change compute fitness. Okay, so we grab the current fitness from the sensor data, and I'm going to comment out this line here, and I'm going to uncomment this line. So if the current fitness is worse than overall fitness, set overall fitness equal to current fitness. So now you're only as good as how well you do in your worst environment. Make sense? Okay, let's run this and see what happens now. Okay, when we run it now, you'll notice that the values return to positive values. Remember, we've removed the log. And we can see that fitness tends to be around 0.1. So in any one environment, the robot, actually, let's take these. So the initial 10 random robots that we started with all get a fitness around 0.1. Right? So a random robot in any one environment, that's about the fitness that it gets. We can see that there's some improvement going on here, but not too much, right? It's only at 0.11, so very little improvement. So clearly we're not showing the behavior of these evolving robots, but you can probably already start to guess what these robots are doing. So before you see what the best robot is doing here when we get to 50, try and imagine what that robot is going to, how that robot is going to behave. And we'll see in about a minute whether you're right. Okay, a little bit of improvement here, but not too much. A little bit more, just at the end. Okay, what does this robot do? Here's how it does in the first environment. Here's how it does in the second environment. Here's how it does in the third environment. And here's how it does in the fourth environment. Makes sense, right? If you're only as good as your worst trial, best thing to do, don't move, right? If you tend to be stimulated by light, you might get lucky and move towards the light in one environment. But if you're generally stimulated by light, in another one of the environments, you're probably going to move away from the light. So by taking the worst case, we've really kind of selected for overly conservative robots that choose not to move at all. Okay, so let's go back to our code and undo this change that we made. So let's go back to individual first and go to the compute fitness function. Instead of taking the worst, we're going to sum up the log of the fitnesses. And remember, we need to make a change not just in individual, but also in population. We need to change how we set the default fitness values. We're setting them to 0 because we're going to sum up those fitness components over the individual environments. Okay, so that's phototaxis. Last thing I want to do today, unless there's any other questions, is to return to this question about evolving morphology. So far in this course, what we've been doing is setting up a simulation in which we can evolve the brains of our robots. But of course, evolution doesn't work like that. It doesn't just sculpt the brains of organisms over time. It also sculpts their bodies, right? Brain and body go together. So I'm going to make a little bit of a change to my code base here to show you how you can actually place not just the brain of the robot under evolutionary control, but also the body. Okay, so let's see here. Let's return to the quadruped. Let's go back to the quadruped assignment. And if you remember in the quadruped assignment, you were creating an engineering drawing of this robot, which you can see here. And again, we've got this main base, and then the quadruped has 4 legs, and each leg has an upper part and a lower part. So for fun, let's let's place the radii of the 4 upper legs under evolutionary control. So the width of these legs can be wider or narrower. Now this particular change to the body probably isn't going to have much of an impact on the robot's overall behavior, but it's just an example to show you how this works. The reason we're changing the radii of the upper legs rather than the lower legs is if evolution makes the radius of the leg larger, then we have to move the whole robot up because the radius gets larger. So I don't have to move the robot if I just change the radii of the upper legs. Okay, so that's where we're going. How do we do that? Well, the first thing I'm going to do is make some changes actually to my genetic algorithm. So if I open geneticalgorithm.py, we can see that at the beginning of my genetic algorithm, I evaluate all the parents, and then I enter into the evolutionary part, and at the end of the evolutionary part, I evaluate the best robot. I'm going to place an exit statement here. So I'm just going to play back the initial random parents, and I'm going to play them back in play paused is false, and play blind is also going to be set to false, which means I'm going to see all of the parent individuals. I'm going to open constants.py, and I'm not going to do phototaxis for now. I don't want my robot to behave well in all 4 environments, just one environment. Okay. I'm going to start with just 2 robots, and I don't need to change number of generations because I don't even get that far in the code. Okay, so what I'm going to do is the genetic algorithm code is now basically just going to create 2 random robots and show them to me. So let's make sure that's what happens. There's 1 and there's 2. Okay, and we should see that these robots are just shown in these 2 environments. Code ends. Here's the fitness of those 2 robots. Pretty straightforward. Okay, obviously these 2 robots look identical, but move differently because evolution is evolving the controller, but not touching the body, right? We made the bodies of these robots, so they're all identical. Let's change that now. Let's go into robot.py. In robot.py, remember a robot is made up by sending objects to the simulator, then sending joints, then sensors, then neurons and synapses. In the objects function, we create the box, the main body of the robot. Then we create the 4 upper legs. Then we create the 4 lower legs. So let me just put a little comment here to remind myself of that. Upper legs, lower legs. Okay, so remember we're going to change the radii of the 4 upper legs. So what we're going to do is change these 4 values, right? At the moment they're just set equal to the radius number, which is stored in the constants file. All right, we want to change those. So we're going to have to give evolution 4 more numbers to play with, right? The 4 radii of these 4 upper legs. Well, where do we store the genetic information for each robot? It's stored in individual, right? So let's open individual.py. Here's the genome. And at the moment, our genome is storing a matrix, a 4x8 matrix, which stores the synaptic weights connecting each of the 4 sensors to each of the 4 motors. Let's leave that alone. We still want to evolve the brain, so we're just going to add something else. We're going to add a new chromosome, if you like, to each individual. And we'll call this radii. We know we need 4 numbers, so we're going to ask numerical Python, or NumPy, to generate some random numbers for us. And we want those random numbers, we want 4 of those random numbers. This will return a value between 0 and 1, so we'll just assume for the moment that radii can range between 0 and 1, and let's hope that NumPy never hits on 0 exactly, or else we're going to have an undefined robot. Okay, so the genome of our robot is now really made up of 2 chromosomes. The first one encodes synaptic weights. The first chromosome encodes synaptic weights, and the second chromosome encodes these 4 radii. Okay, we have them. We now need to send them to the simulator, right? So we do that in this function, start evaluation, right? We need to send those radii. So you can see here that when we create a robot in the simulator, we're going to send this genome so that it knows which synaptic weights to send to the simulator. So we're going to add an argument here, which is self.radii, right? We're going to use that information in radii when we build our robot in the simulator. Okay, so we're leaving individual, and we're now going to open robot.py. We now have to add radii here. You'll notice that genome is now called weights in here, just to remind me of where this is going. These radii are going to be needed by the objects. Joints, sensors, neurons, and synapses, they don't care about the radii of the objects themselves. I need to add that argument down here. And I'm now, oh, it didn't save my change. Remember that these are the upper legs, and these are the lower legs. Okay. And remember, we're after these 4 numbers here. So we're now going to erase them and replace them with the first value in the radii vector, second value in the radii vector, third value in the radii vector, and finally the fourth value in the radii vector. Remember, in computer science, we always count starting from 0. Okay, so when we create the 4 upper legs, the radii of those legs are being pulled out of this vector, which is the second chromosome of the robot. All right, I think we're good to go. Let's see what happens when we run this now. Okay, we saw something crazy happen. Why did we see something crazy happen? Because apparently 0 to 1 is not a good range for our our robot here, right? So how do we know what range we should use? Well, let's go back to constants.py, and you'll notice that the length of any one leg segment is 0.1. So let me go back to my engineering drawing. So this length here is 0.1, and the radius is 1/5 that, right? So this length is 0.1, and this radius is, what is that, 0.02, 1/5 of 0.1. Okay, so 1 is probably not a good choice. Let's instead set the radii of these to be, what did we say? This was what did I say, 0.02? So let's say between 0.01 and 0.05. 0.01 and 0.05. So min radius equals 0.01 and max radius equals 0.05. Okay, so evolution can set the radius of any upper leg segment to a value in there. Okay, we have to go back to the genome of our robot, which we know is stored in individual.py. Here are the radii. We know that NumPy always gives back values between 0 and 1, so we need to take these values that range between 0 and 1 and scale them to a range of 0.01 to 0.05. So how are we going to do that? Well, let's see. We want, so 0.01 to 0.05, we need to divide by the range first. So that's constants dot max radius minus constants dot times min radius. Right, so we're dividing, I'm sorry, we should be multiplying by this range, right? So this range is 0.05 minus 0.01 is 0.04. 0.04 times values in 0 to 1 give us a new range of 0 to 0.04. And we need to then just add the minimum radius. Right? Minimum radius 0.01. So now this whole thing will give us random numbers between the range of 0.01 and 0.05, or between the range of min radius and max radius. Okay, let's run our genetic algorithm again and see if we're in the right ballpark. Aha, this is looking much better. Okay, so we've got some much more muscled robots now. They've got some pretty big biceps on them. Okay, so now we can see, obviously, we have a population of 2 robots, and each one of these robots has a different brain, because they're moving differently, and a different body, right? And both of these are under evolutionary control. Okay, I think we're good here, right? Looks good to me. Okay, so are we done? Well, the answer is we're not actually done yet because, oops, I think I deleted my terminal. Let me open up a new one. We're not done yet because we've encoded those radii in the genome, but we haven't allowed evolution to change the genome over evolutionary time. Right? Let's go back to individual.py. So we've got our genome that's made up of 2 chromosomes, but whenever this individual is mutated, we notice that it mutates an element in the genome matrix, right? It's changing one of the synaptic weights. So that's fine, but we'd like it to also be able to not just mutate the brain, but also mutate the body. So let's define a new function called mutate brain, which we already have, right? This function will mutate a part of the brain. And let's create a new function called mutate body, right? So if this one is called, it mutates the body. Otherwise, it mutates the brain. And now what happens when an overall robot is mutated, right? We're going to mutate the body or mutate, we're going to mutate the body or mutate the brain. How should we decide which gets mutated? Well, let's assume that whenever a mutation occurs, it's going to mutate one part of the body and then one part of the brain. So every new mutant is slightly different morphologically and neurologically from its parent. Okay, so we now need to make a change to body, right? We need to pick one of the 4 radii to change in the same way that we picked one random synaptic weight to undergo evolutionary change. Okay, so we're going to pick a random integer between 0 and 3 inclusive. So the 0th, 1th, 2nd, or 3rd radius. And then we know that that's stored in radii r, and we're going to set it to some new value, self.radii r ... So if the radius changes, how should it change? Let's just set it to a new random value between the minimum and maximum range. And we already know how to do that. We've done this already here. So let's borrow this piece of code. Let's borrow this piece of code and place it down here. Okay, so we need now, again, a random number, just one random number, because we're just mutating one radius, and we're going to scale it to a value between 0.01 and 0.05. Okay, so now whenever a robot gets mutated, one radius is randomly selected, and its radius is changed. Or sorry, one upper leg is chosen, and its radius is changed. So actually, maybe just to remind us of that, let's call this UL for upper leg. So the radius of that upper leg is changed to this new random value, and then the brain is also changed a little bit. Okay, so I think that's it. We placed the body under evolutionary control. Let's go back, let's run our code again. Okay, we can see that we have our population of 2 robots, and each one has a different body and a different brain, but we can't really tell. There's no evolution going on, right? These are just the initial 2 random parents. So let's go back to geneticalgorithm.py, and we will allow evolution to run now. So we're going to turn off the graphics, play blind equals true, and we're going to iterate through our genetic algorithm. Let's open constants.py. And let's use a population size of 10 again, and number of generations is equal to 50. Okay, let's run our code now, and let's see what we get. So the interesting question that we can ask here is, does it matter that those 4 radii are being changed by evolution? By changing the radius, we do change the mass distribution of the robot a little bit. Each of those, here we go. Okay, not bad. So a robot with a thin forward and back leg and a thick left and right leg. Let's open up our genetic algorithm a little bit more. Let it run for 100 generations rather than 50. So we saw that we got this one morphology where we had a thin front and back leg and a thick left and right leg. So was that just by chance? Did evolution happen to hit on that, or was that actually a useful adaptation? Well, how would we know? The way we would know is by running our genetic algorithm many times. And remember that every time we run our genetic algorithm, we start with a different random population of robots. So if the final evolved robot keeps converging on the same morphology, that seems very unlikely unless that morphology happens to be useful for the task at hand, which in this case happens to be walk towards the light source. Let's see what we get this time. We get a very different morphology. And not bad locomotion, actually. Let's run it again. Let's see. So we now have done 2 different runs and got 2 very different morphologies. It suggests to me 2 hypotheses. So either morphology just doesn't matter for this task, that we can evolve a robot that walks towards the light source regardless of its body, or that there are different good morphologies. Tricky. Maybe there are different kinds of morphologies that work well for this task. Let's see how we do this time. Very different morphology yet again. So the front and the left leg are wide and the right and back are thin. Let's run it one more time. Okay, starting to look like at least one of our hypotheses, which is that there is one good morphology for this task, is invalid, is not true, right? We're running evolution, getting lots of different solutions. Okay, so I showed you how to place the 4 radii of the quadruped's upper legs under evolutionary control. Hopefully by walking you through that process, you'll start to have an idea how you could place other aspects of the robot's morphology under evolutionary control. So how would you, for example, well, let's see what we come up with here first. Okay, a different morphology and a different way of moving yet again. Okay, so probably there is no one right way to do this task. There is no one right morphology for this task. Okay, so what I just showed you is parametric change, right? We changed some of the parameters of the robot body. What about topological change? So topology means we're actually adding and removing pieces. So how would you change your existing code base so that evolution can add and remove legs? Or maybe add and remove segments. So maybe a leg is made up of 2 segments like we have here, or 3 segments, or 4. How would you add fingers or toes, for example? Could evolution start to add branching structures onto the ends of these legs? That's a little bit more challenging and takes a little bit more coding and is probably beyond the scope of this course, but might be something worth investigating. Okay. I think that pretty much covers everything I wanted to talk about today. We have 9 minutes left. Unless there are other questions, we might finish a little bit early today. Okay, so just before we wrap up, then just a reminder about the schedule and the course home. You can always find us at reddit.com/r/Ludobots. If you're new, you can start here, work your way through our programming assignments. If you do click on the stickied link here, you will see a series of links. The most important one for us is probably the schedule. If you click on the schedule, you will see what's going on here at the University of Vermont. We've had 8 lectures. We've had 8 lectures so far. And we're moving on to lecture 9 tomorrow morning. If you've missed the lectures, you can go back and watch all the videos and do the assigned reading and obviously follow along with the the assignments. Okay, I think I will sign off there for today. Good luck, and we'll talk to you all next week. Bye-bye.